Hello, everybody. Welcome to our August ambassador meeting and presentation. I'd like to introduce Kareem Sarathia from APL, who studies synthetic aurora, and I'm very excited to hear more about that. Over to you.
Yeah, so let me dive in. So I'll be talking about using computer models to build synthetic aurora, and I'll explain sort of how and why we do that. Yeah, so let me start by just saying a little bit about myself. My name's Kareem Sarathia. I'm a geospace scientist at Johns Hopkins Applied Physics Lab. I work at the multi-institution NASA Drive Center for Geospace Storms, where we've been working on developing a geospace model we call MAGE for multi-scale atmosphere geospace environment. And it's always a fun excuse to have new logos and model names and acronyms and all of that. In terms of my background, my PhD is in applied math, and sort of my doctoral research was on using supercomputer models to study the sort of spinning plasma around black holes, but now work in sort of geospace and heliophysics plasma modeling. I should probably get this out of the way right off right off the bat. Despite the fact that at this point I've written several papers about sort of the magnetospheric drivers of the aurora, different auroral forms, I've never actually seen the aurora in person, but I hear good things. I'm looking forward to hearing more about that. Um, so in terms of what I'll talk about, and like I said, please feel free to interrupt and ask questions. We can have a conversation. I'll say a little bit about sort of an overview about geospace, what it is, and why we care about it. Then talk a little bit about sort of specific modeling that we do, and then finally you look at some specific examples of sort of using these kinds of geospace models to understand what's happening in space to cause the sort of shapes that we see in the aurora. So, of course, to start with, you can't talk about what's happening in the space near Earth without talking about the elephant in the room, which is the sun. Um, Geospace doesn't exist with a vacuum. Metaphorically speaking, of course, literally speaking, most of it does. But it's very much affected by the environment created by the sun. Most of sort of geospace is understanding the interaction between the solar wind and the Earth's magnetic field. And so here we have this simulation we've done here at APL of a coronal mass ejection coming out of the sun. And you can see sort of just this massive, massive structure that's sort of heading out into the solar system. And I don't, can you see my pointer? Maybe.
Yes,
Yes.
we can.
Yeah, so if you look very closely, you can see this little blue dot here, and that's Earth. And so it sort of gives you a scale of what's happening in these coronal mass ejections and how that's really interacting with this little tiny dot out there that is our magnetic field. So as we sort of switch to the other side of this interaction, the solar wind actually interacting with Earth, uh, let me show you sort of a little bit of a visual tour of geospace. And since I'm going to show a lot of these three-dimensional images, let me try to explain here what I'm showing. So in this case, I have the sun is off to the bottom left, and so the solar wind is going from the bottom left to the upper right. I'm showing these traced three-dimensional magnetic field lines, and I've cut a plane through the magnetic equator. So the normal to that plane is going to be the north magnetic pole. And we're sort of looking down from above the equator, say, if this towards here is noon, this is dusk, this is midnight, this is dawn, we're sort of above the plane looking down, sort of between noon and dusk. And like I said, feel free to ask questions. Let me know if something's not clear. What I'm showing in this sort of false color image is the strength of the magnetic field compared to dipole. So orange means that the field at that location is stronger than the Earth's dipole. Purple means that it's weaker than the Earth's dipole. And so we can sort of see here that the solar wind comes smashing into the Earth's day side, that compresses the magnetic field and creates this strong field region. We'll see that during these kinds of substorms and stretching events, the magnetotail stretches and becomes weaker than dipole. And so this is sort of this overall global picture of the magnetosphere. We can sort of look at some of these different pieces that as the solar wind comes smashing into the day side, that creates the bow shock as that's abruptly decelerated. It creates this shocked hot plasma of the magnetosheath, and that's separated from the interior of the magnetosphere by this magnetopause that sort of separates the closed field lines from the sort of hot magnetosheath plasma. So going in a little bit more, we can see here, this is the hot plasma of the ring current in the inner magnetosphere that is enhanced and protects Earth during strong storms. These are field-aligned currents, so currents that move up and down the field lines to connect the magnetosphere to the ionosphere. We can see sort of as we move in further, I think it'll move in further. Yeah, we sort of zoom in further and going into sort of the upper atmosphere, the ionosphere, and the thermosphere, and down to the lower atmosphere. And you can sort of see, of course, again, just how thin that shell is compared to the sort of global spatial domain of the magnetosphere as a whole. But to actually understand what's going on, we really need to understand all of these different pieces and how they interact, especially to create this sort of first principles model identification. So that's sort of what geospace is. Why do we care? And the reason we care is that increasingly it's the case that space is where we keep our stuff. So I'm talking to you about magnetospheres, thermospheres, ionospheres, and all these spheres. And so this is a visualization that was done using one of our simulations. It was done by the Hayden Planetarium, and they did a really awesome job. And one thing I thought was really cool is what they did was they added this sort of these green dots to represent what they call the technosphere. Each of these green dots is a satellite. And what you'll see is, as I show this animation, how sort of precarious that sphere of technology starts to look, that sphere of technology that we really rely on, starts to look during a geomagnetic storm. So here, this is coming in. We'll see the magnetosphere during a geomagnetic storm. So red is showing the currents, the densities. You can see in that sort of, I don't know, turquoisey color, the magnetic field lines. And it'll zoom in and we'll start to look at the actual individual spacecraft in that sort of green technosphere thing. I think it's about to show up here. And then in a few minutes, in a few seconds, you're going to see this very strong coronal mass ejection impact Earth, just right now here. And you can see again, like I said, just how precarious that all starts to look. All of this technology that we rely on starts to look during these storms where we have sort of the solar wind kicking down our door. And of course, just how much there is sort of throughout space. So going further, one of the reasons we care about space, and obviously, I think a lot of us here care about space just because it's cool, but one of the pragmatic reasons to care about space is because of these kinds of space weather hazards. There's energetic particles that come from the sun and exist in the radiation belts. Often, so the ones in the radiation belts are often called these sort of killer electrons that can damage spacecraft, can cause hazards to astronauts and even people, on planes over the polar caps. Ionospheric irregularities can affect communication and navigation. Variations in the currents in the ionosphere create variations in the magnetic field on the ground, which can actually create these geomagnetically induced currents that can damage and disrupt the power system. And of course, as we dump energy from space into the atmosphere, it sort of puffs up like a souffle, and sort of satellites that were in space are now not so much, which means there's a lot of drag and potentially can actually cause early deorbiting of a lot of these low Earth orbiting satellites. And, I think a famous example of that is the SpaceX storm, where a whole bunch of them just sort of fell out of the sky. So that's sort of this rough overview of what geospace is. How do we model it? Let me start by saying, why is it hard to model? And one of the reasons is that it's sort of this tyranny of scales. Geospace is this multi system of systems, spanning the magnetosphere to the upper atmosphere, the ionosphere, thermosphere, all the way down to the lower atmosphere. And in each of these systems, there's different characteristic scales. The magnetosphere is gigantic, 1,000, tens of thousands of kilometers, down to, hundreds of kilometers in the ionosphere, the upper atmosphere, down to single-digit kilometers in the thermosphere. And to have a first principles model that can connect all of this together means that we have to capture all of the processes happening at all these different scales and how they interact with each other. So this is a multi-scale system. It's a multi-domain system. It's also a multi-physics system. The physics we care about in the magnetosphere, the sort of large-scale fluid-like plasma, is very different than the chemistry and neutral physics that we care about in the lower atmosphere. And so we have to kind of capture all of this in one big model to really see this fully interactive picture of geospace. So how do we model a system of systems? Well, it's kind of a whole thing. Um, so I'm showing here on the right one of these model coupling diagrams that I kind of hate, but it gives a useful sense of why this is such a complex thing. So this is all these different submodels under what we have this sort of umbrella of what we call the MAGE model or MAGE model. Um, and to capture a system of systems, we need a model of models. Each of these models has its very specific physical processes, its own domain. We have a model of three different ionosphere models, one for the high latitude ionosphere, one for the low latitude ionosphere, one for just the electrodynamics of the ionosphere. We have fluid plasma models for the larger global magnetosphere domain. We have more kinetic plasma models for the more energetic particles, plasma of the inner magnetosphere. So, to model geospace, we have a bunch of these coupled geophysical models. We need large supercomputers. We typically use supercomputers at NASA and the National Science Foundation. We need specialized algorithms to solve the relative differential equations in each of these different domains. And so the result is why we have these kind of multi-institution science centers. We model a system of system with a team of with a model of models, and to create that, we need a team of teams. We have a team of experts spanning, plasma physics, the different geophysical domains, but of course also software engineers, computer scientists, mathematicians, and even data scientists. And I think that last point is also really important because after all of this work, we can run this supercomputer simulation, and what you end up with is just, terabytes of numbers. And so actually being able to turn that final output from the model into, meaningful scientific insight is its own problem. And I think one that really does need a lot more work devoted to it. So I'm certainly not going to go through the details of all these models, but I'll just sort of show one of these as a sort of representative example. This is I'm seeing some stuff in the chat, so I don't know if there's any questions or something, just interrupt me. This is what this is our model Gamera. This is a magnetohydrodynamic model, which sort of models plasmas in this sort of large scale fluid picture. And I always like this quote from XKCD, which sort of describes MHD as a combination of the intuitive nature of Maxwell's equations with the simple solvability of Navier-Stokes. And this is our model called Gamera, which has this background attached to it, but really it was just an excuse to use a mascot that was one of these old school Japanese monster movies. But this is just one of these pieces. And again, each of these individual models have a lot of its sort of own expertise in development, a team working on just this model, which we then have to integrate into this larger model of models and all this sort of collaboration and interaction that goes with that. So putting this all together, here I wanted to show an example of sort of this feedback loop, why it's so important to really capture the interaction of all these different domains and how they feedback on each other. So this in the top right, so let me also say the orientation of these are a little bit funny, but they're done in such a way that the sun is all sort of to the bottom left here. I'm showing at the top again the sort of three-dimensional visualization of the magnetosphere with a cut through the magnetic equator. Red means the field is strong, black means the field is weak. So again, you can see on the day side, compression of the field from the solar wind creates a strong field. The stretching of the magnetotail on the night side creates a weak field. And here we have an example of a southward turning of the solar wind. That's going to start to create reconnection on the day side. That's going to start to stretch the tail in the substorm growth phase. And pretty soon then what will happen is we start to get these localized bursts of reconnection. That localized reconnection sort of creates this slingshot effect where plasma on those reconnected field lines gets snapped back towards Earth and launches this plasma into the inner magnetosphere. And that plasma that launches into the inner magnetosphere becomes energized, and energetic plasma starts to behave very differently than the fluid version of it. So here I'm showing a sort of similar animation. This is again cut through the equatorial plane, and I'm showing individual energetic particles. Blue means lower energy, and purple means higher energy. So these energetic electrons get shot from the plasma sheet into the inner magnetosphere and accelerated, and they'll start to drift around Earth, from drift westward, eastward around Earth. And as that happens, we have now these energetic particles in the inner magnetosphere. They will interact with waves or get scattered or various mechanisms, and that creates precipitation. and those electrons will then precipitate into the atmosphere. And that's the core of what we know to be sort of what causes so much of the aurora, is that initial precipitation of these electrons into the atmosphere. And so now going over to this last plot over here on the bottom left, this is showing the energy flux going into the ionosphere from these precipitating electrons. So this is just showing how much energy is there in the electrons that are total energy that's coming from the electrons falling into the atmosphere. And you can see here, this starts, you sort of quiet time auroral oval. This is, oh, actually, let me show this again really quick. This is just to show here, this is the sun at the bottom, dawn and dusk over here. So again, as stuff starts to happen, we see these flow bursts coming in from the magnetotail. That's going to create these torch-like structures on the auroral oval, these streamers. And then you can also see how those elongations will then start to drift uh, eastward and westward, depending on where they're going, based on the ambient convection and energetic particle drift. As this energy input is happening into the atmosphere, that creates ionization. That ionization will then affect how the currents that connect the magnetosphere to the ionosphere will close, which then in turn affects the overall convection, which is how these magnetic field lines are moving throughout this very large, 100,000 kilometer domain in the magnetosphere. And so again, we have this sort of very large feedback loop that has to go, sort of goes around and around that connects these two systems together. And so as an example of that, this is a simulation of the very interesting recent event, the often called sort of Mother's Day or Gannon superstorm on 2024. And we sort of see an extreme example of a lot of this feedback loops here, where the solar wind is exceptionally strong and really, really pushes in on the day side. And as a consequence of that, these reconnection and flows from the magnetotail really get launched very, very close to Earth, building up the very strong ring current that characterizes these strong storms. And so this is, again, a very interesting event, one that we have been looking at quite a lot, just because it's so unique. This is, I think, the strongest storm in 20 years or so when it happened. So I guess as a last step, having shown us sort of a little bit about how we do this modeling, what can we do with it? Uh, and this comes back to the sort of actual synthetic aurora. And what do I mean by that? Um, the synthetic aurora is not going to be as nice as a real aurora. The real aurora is pretty good, right? Um, so what I'm showing here is, again, in this case, the sun is to the right. This is showing what's happening in the magnetosphere. And this is showing the energy flux coming from the magnetosphere, the energy flux in the precipitating electrons coming from the magnetosphere and landing in the ionosphere. And I want to make clear, this is a false color image. This is not, supposed to be a reflection of what you would see with your eye. This is just showing that sort of energy, but I did put it in a, nice green color bar to make it sort of aurora-y looking. But there's a lot of extra physics and photochemistry that happens from just how many and how energetic the electrons are that are precipitating in terms of going from that to what do you actually see with your eye, as far as the actual auroral emission and what altitudes and all of that. But we can actually look at this and see what happens. I should also say, in this case, the sun is staying on the right side, so that's why you see the Earth rotating underneath it. And then we can see as stuff starts to happen in the magnetosphere, how that gets reflected in these structures in the night side aurora. And in particular here, we have some sort of weak flows, some of these weak bursty bulk flows that are coming from the magnetotail. But as this starts to become more and more intense, you can start to see a lot more structure. And particularly as we go into the sort of full substorm phase, and there's lots of flow coming from the magnetotail towards Earth, we can see a lot more of that kind of structure. So one thing to make one thing to make clear, you all are used to seeing the aurora on the ground, and you can sort of mentally imagine. You can look at the variability and the spatial scales of the aurora that you see, and mentally project that to a map like this. And when you do that, you realize that this aurora is very chunky. It has this sort of 8-bit Nintendo looking way about it, which is obviously not what happens in reality. And that's just a reflection of the fact that even with supercomputers, our ability to really connect what's happening over these massive, massive domains to what's happening over these very small domains is still limited. Um, and so, we can use these models. So I guess the point I want to make, or point I hope I can convince you of, is that even though these models are obviously imperfect, they can still be very educational to help us understand how to connect what's happening in space to the aurora. Why do we want to do that? Well, there's a massive amount of information about what's happening in space contained in the aurora. What you end up seeing on the ground is the result of what's happening over a massive spatial domain where we have very, very few spacecraft and in situ measurements. So we would love to be able to use that information in the aurora to understand what's happening in space, but it's like sort of, trying to predict if you see the shadow of something, how do you reconstruct what is actually creating the shadow? It can be quite difficult to invert that information to really understand what's going on. And so this is where we hope that modeling can help us sort of build this Rosetta Stone to better connect what we see in the aurora to what must be happening in space. And that's been our goal for a lot of this kind of modeling work and sort of synthetic auroral proxies. One example of that, we did this early on. I think one of the first studies we did with our new model was auroral beads, which are often associated with substorm onset, forming on these sort of wavy arcs that form early on in the substorm growth phase. This is showing here an example of from ground-based imaging, and then this is showing a synthetic version taken from the model. And what we showed here is that we could actually reproduce the spatial structure of these auroral beads with this global modeling, although, there's certainly still kinetic details that we're not quite nailing down yet. And I can show you sort of how we did that. Here on the left, this is showing a three-dimensional picture of the simulation. This is the day side on the right, night side on the left, and we can sort of look at these different layers of zooming in. So here in blue, I'm zooming in to get this, and you can see these individual, what are called ballooning interchange heads. It's sort of a plasma instability that develops, and just how small this is compared to here. If we zoom in again, you can see just one of these individual ballooning interchange heads, and we zoom in yet again, you can actually see here, each one of these is a grid cell in the model. And so for each one of these grid cells, we solve that system of nonlinear differential equations. And so if you can imagine mentally unwinding this, so going from this to this back to here, how many grid cells there must be in this massive spatial volume, and how we have to solve in each of these complex equations. And so that's why we need these big supercomputers to do these kinds of calculations. But showing this over here, this is again showing this sort of equatorial cut, the non-dipolar part of the magnetic field. So this is strong, this is stretched, and this is showing what happens as we go into a substorm growth phase around 8 o'clock. As we have this turning in the IMF, there's reconnection happening on the day side. Magnetic field is getting pulled from the night side towards the day side. And as that happens, you create regions of weaker and weaker field, which is where you can create the exact kind of environment where these plasma instabilities can grow, creating these sort of ballooning interchange structures that then get represented in the aurora as these spatial structures consistent with auroral beads. So that's one example. Omega bands, I think, are another interesting example. These are these undulations on the poleward edge of the auroral oval. You can see sort of an example from data here. And they're also interesting from a space weather perspective because omega bands on the dawn side auroral oval have often been associated with strong variability in the magnetic field observed on the ground. And that's interesting because it's exactly those kind of what are called geomagnetic disturbances that can create the right create the right conditions to cause to disrupt the power grid. So understanding what's causing that and why is really helpful as far as being able to protect the power grid. And so what we did here was showing that in this case, these dawn side omega bands, what happened during storms because of these very intense flow bursts coming from the magnetotail and sort of smashing into the dawn side inner magnetosphere. I can talk more about the details of that, but in this case, we could sort of see why this is showing how sort of structured the different currents are that are then going into the ionosphere, and how these different sort of individual different fingers of flow coming in are attached to this sort of omega band torch structure over here. So that's another example of connecting that. And this is actually more recent work. This was how I originally became familiar with some of the Aurorasaurus work. is I was interested in this specific event because I had seen some of the University of Calgary T-Rex images, and I'd actually gone on Aurorasaurus to look up the same date range for this event, and found this really beautiful photography done by Gunjan, who was very kind enough to share all of this with me, and is now a co-author on this paper. But I sort of, it reminded me quite a lot of that classic Prince song. So I sort of been just referring to this as Purple Rain coming off of the Green Aurora. What we found is we looked at data and we found that this low latitude purple aurora was happening at the same time as we saw a enhancement in the very energetic electrons of the radiation belt. So these energetic electrons of the radiation belt are often called sort of killer electrons because of the damage they can do to spacecraft. And so we found that the emergence of these sort of low latitude purple flashes was happening at the same time as these enhancements in the killer electrons. And so going to modeling, we were able to look at the same event in modeling and show that the reason we were seeing this connection is that we were getting reconnection happening unusually close to Earth during the storm time event. And that was able to sort of very effectively launch these flows into the inner magnetosphere, which then dragged a higher energy particles from the plasma sheet and enhanced the radiation belt. So again, this is just another example of how we can sort of use some of this auroral phenomenon to have a better understanding of what's happening in space in general, but then also potentially having a better understanding of what's happening in space that could potentially be a space weather hazard. So I think that's sort of the main stuff that I had prepared, but I'm happy to chat and answer questions or ask questions, all that kind of stuff.
Thank you so much, Kareem. This is absolutely fascinating, and I really, as a non-scientist, I really appreciate how understandable all of this was.
Thank you.
I have learned so much. You had talked a little bit about using Aurorasaurus and talking with Gunjan on your paper, which is fantastic. But I was wondering, to continue the nerd model, what are some other ways that citizen science, participatory science can support CAST for MAGE and these other models?
Yeah, so I think there was definitely been very interested in what you can do with that kind of stuff. I think sort of off the two things that occur to me, and again, I'm not necessarily an oral
Sure,
person
sure.
in general, so much as a modeler in general. So this is very much from my perspective, but sort of two things is one is a data product kind of
Hmm.
collation of that Aurora source data. So for instance, one thing I'm often looking at is I have a large scale Aurora oval in my model, and
Hmm.
I don't know if it's in the right place or not.
Great,
Could
yeah.
I get from Aurora source, just from all the different individual measurements, some actual latitudinal line of what is the auroral boundary that I can compare with my model? That would be awesome.
That'd be really cool.
And then I guess the other thing is, in a lot of events, I might say, this is the event I'm interested in. Let me go poke around Aurorasaurus. And it's kind of, you sort of go in manually, you kind of go in around and click on the map and see
Hmm.
here's a picture, here's a picture, here's a link from that to Twitter. If there was some way of having an API where I could
Yeah,
just have a Python script that says, this is the latitudinal range I'm interested in, this is the date range I'm interested in, here's the figures I could quickly go through, that would also be really amazing as a way of interacting with that data and seeing, what can I use to add more context to the scientific event that I'm interested in.
absolutely. Absolutely. And I would let Liz speak more to that, but we'll have to have that conversation offline. Joe, did you have a question?
I do actually. Were you just calling on me randomly, or did I look like I needed one?
No, you turned your camera on. That's the giveaway.
Oh, I'm just trying to be polite and be part of this.
Yeah,
But yeah, I was wondering, and I'm sorry if you said it and I missed it, but um, I'm wondering, do you have anything in the model yet or envisioned that would account for, I guess, photometric concepts? In other words, how the eye sees color.
Yeah,
So
so
we can calculate radiation at different wavelengths, but then we have to model that. We have to weight that by the human eye response, the photometric response function to get what a person would see. And I
exactly.
didn't quite catch that if you talked
Let me
about it.
see. I threw in a bunch of extra slides in case they came up, and it seems like I did
Ah,
not. a very good job of picking the right
Yeah,
ones.
there you go.
That one, this one's probably not helpful, but I like it anyway.
I I
Um,
saw the note on one slide about red plus blue is purple, and I'm glad you're talking about that.
you don't want to know how long I actually, because again, I'm not an oral person at all. I'm a mathematician by training, so just learning, like when I was interested in this purple aurora event, even understanding exactly what was causing that was
Yeah,
actually a whole separate thing.
yeah.
Let's see if I can find it because I think that's a really interesting point, and it's something that we have been looking at. Um, which is, how can we better connect? So, I showed you this synthetic auroral proxy
Uh-huh.
here, which is just the electron energy flux. And I know the characteristic energy of the electrons that are precipitating. And what I can do is use an auroral transport model. There's one called GLOW. There's actually one being developed by the University of Calgary by Jun Liang, who does really amazing work and has actually been very helpful in helping me with this kind of work. And what they do is, if you give them the spectrum of precipitating electrons, they essentially have a column of neutral atmosphere. They shoot them through,
Mhm.
scatter around, and then they can predict the emission of different color wavelengths at different altitudes. And you can go both ways. So we could take our data that just tells you the specifics about the precipitating electrons, and they can make a prediction of the visual emission from that. But what's also really cool, and I'm happy to let them do because I think they know this much better than I do, is that they can take the stuff that they see in their RGB cameras and their spectrographs and invert it exactly to the same quantities I would be putting into my model, which is namely the energy flux total and the average energy of the electrons that are coming in.
Okay, so they must be accounting for the photopic response function and stuff like that, because otherwise, like a spectrograph and a camera, they measure very different things.
Yeah, I
Because,
know I remember somebody showing me this very, this very, getting very much into the details of, what is the color response graph for R, G, and B, and how that
Mhm.
maps to the individual spectrograph lines. And that's then starts to become, it becomes a whole thing. And
Yeah,
is well outside of my specific area. But yeah, like, again, just trying to connect all these different lines to then how that gets responded, how that responds to each RGB channel in the camera. And then,
exactly. Yeah. Cool.
yeah.
Thank you.
So
Good luck.
I think that's a really cool area. I think there's a lot we can do in terms of better connecting the data and the modeling through that. But also, there's a lot we just need to do on the modeling side to get there as well. We still have a long way to go on the modeling side to capture all the right physics and actually get to those right scales as supercomputers get better and better.
Yeah, no, you got your work cut out for you. Nice
No,
work. Thank you.
I have a lot of reasons to be continuing funding is I think what you meant to say.
I just wanted to pop in and say that I put an article in the chat. I think this is the one that I've read before that talks about the RGB cameras for T-Rex specifically, which is the Transition Region Explorer network of all sky imagers and how they deal with the RGB cameras and then converting that into like a specific color channel,
Mhm.
like a 557.7 nanometer classic
Yeah.
green light aurora. So that one might be interesting to check out, Joe, that paper.
Yeah, for sure. And that's what I was talking about. I was wondering if he was doing that sort of thing in the model, because yeah, this is all great. Thank you.
Of course, thank you.
That's so fascinating. Thank you. I have another question. Um, can and you may have covered this and I missed it. But this is the model seems to be really focused on electron precipitation. Have you ever modeled Steve's or SEDS with it?
So I think this is something that we're very interested in. I think we start to get into, I think it's definitely a topic we want to explore more, but I think there's a lot more, the spatial scales start to get a lot smaller, and then you start to get a lot of, at least is my understanding, a lot more of the thermal emission and the, um, I guess, multi-component plasma interactions that can get then very difficult and more complicated to model, which we are not currently. I think trying to create the precursors to what would cause that kind of thermal emission, I think is really interesting from our perspective and something maybe more near term. But longer term, I think capturing that full range of physics that would happen for the thermal emission is still something that we would have to work on. And again, this all goes back to this tyranny of scales. The range between, let me see, do I still have it up here somewhere? Just the range between all of this is big. And supercomputers are big, but not big enough.
Thank you so much. Maybe that's something that as technology advances, we'll be able to do.
Oh, absolutely. I think,
Love that.
computers are only getting better.
Yeah.
Our technology, our tools that we can use on these is only getting better as far as, machine learning, gray box modeling, lots of different things that we can do. And I think a lot of exciting options on the horizon.
Yeah. Thank you. Jeremy, did you have a question?
Uh, yeah, I'm not sure how to say it exactly, but thank you for the presentation. It's always great to see something. You can just imagine how much math goes on behind the scenes to get to the point of a visualization and what you choose to show
Yeah.
and what you choose to make, say, transparent or invisible, or where you make your cuts to see how to explore the data visually.
Yeah.
So the two questions would be, how do you approach visualization of your data when there's so many choices of how to look at it, how to color it, how to slice it, timescales? And the second question is, how sensitive are the outcomes of the models to initial conditions? Kind of like, they can't predict the weather more than a few weeks out, depending on the scale. Does that same thing sort of apply to space weather, from the CME all the way to
Yeah.
the individual structures that are seen in the aurora ovals? Thanks.
Yeah. So those are two great questions. So let me go one at a time. As far as visualization goes, it is a big challenge because, not only is it the difficulty of trying to create these three-dimensional visualizations, but when we do these simulations, it's terabytes of data on a supercomputer in Wyoming or something. Working with that data is already complicated because it's massive. If we run a simulation with tens of thousands of compute cores, even doing post-processing, even doing analysis, doing visualization still can cost easily hundreds of compute cores. It's a lot of compute and computation and work that just goes into doing any of that. Then in terms of figuring out what quantity we work with, we have sort of our standard canned plots or animations that we do, sort of kitchen sink, show everything, and let's see what looks interesting for this specific event. But then, of course, it just gets very specific. Each different science application, each different science investigation might need to start to focus on different things. And we all want to try to get at, some of these core things of how does energy move around from domain to domain? What are the different processes that connect the magnetosphere to the ionosphere in these different configurations? And how does all that work? So it gets very I mean, I always hate answering a question with "it depends," but it starts to become very specific to the scientific application. And then as far as visualization goes, I think our most successful examples by far have been when we've worked with people who are professionals at that. Like working with the Hayden Planetarium was a great experience. They did really great work, far, far better than anything I think we would have done on our own. And so it's really great to see, not just the data that we can do modeling wise, but then also really put into these pictures that I think can help people understand why it's important, why it matters, why it's, so neat. And then your other question was very good, and I'm sure I'm going to remember it again in a second.
Sure, I'll just try and, I didn't articulate it very well, but I guess using the idea that you can't predict the weather too far in advance. What is the sensitivity to initial conditions of the outcomes of a simulation? Are you seeing some consistencies in behavior at certain scales, but then some things that sort of never repeat twice with even minor changes in initial conditions, whatever scale those may be? Thanks.
And so I guess the answer is it's in the middle. But one thing to keep in mind, and I think this is a really fascinating distinction between what we do when we talk about space weather and what we do when we talk about terrestrial weather. Earth is very well monitored. We have sensors everywhere. We have satellites looking at all of it. And so when you run a weather simulation, you have lots of data to constrain the initial conditions. And the boundary conditions, what's coming in from outer space aren't that varying for the lower atmosphere, or maybe not hugely. Space is big, and the number of measurements we have in space is very, very tiny as a fraction of that volume. So when we talk about our initial conditions, they almost never have anything to do with the actual system initial conditions, right? We just don't have enough information to constrain the initial conditions of a model. Um, that said, it is also true that the sun is a very strongly driven system because the solar wind is really pushing what's happening there. And that slightly reduces, I think, the importance of initial conditions, at least in certain cases. Um, but at the same time, we also just don't know the solar wind very well. We have one point measurement at the L1 Lagrange point that tells us sort of the solar wind. Um, and that's imperfect. So, we have a model that has the wrong initial conditions, it has the wrong boundary conditions. And if I'm being honest, right, we have to still use somewhat simplified models, somewhat simplified physical approximations. So we have the wrong PDEs as well. So all that said, there is a lot of that sensitivity. I think the amount of that sensitivity depends on the event. So, for instance, when you go to an example like this massive superstorm, if you hit the magnetosphere with a sledgehammer, it's going to act like you hit it with a sledgehammer. And maybe in that case, I don't think the initial conditions are as important because it's just so strongly driven. But maybe some of these isolated substorms where what's already happened at Earth and what's happening are more important in sort of nudging the system one way or another. I think in those cases, the initial conditions are probably more important. Hopefully that answers your question.
Thank you very much.
I have more questions, sorry. Um, so with really big models like this, my understanding is that things like this and KP and so forth are kind of run a little bit out of sync with real time just because they're so big. What are some things in, your, wildest dreams that would help you to run this in real time?
So, there's a lot of different model configurations we can run. It's not like we have one version. So, for, this simulation that went to the Hayden Planetarium was a high resolution one. And so that is more expensive. But
And
we
high
can run,
resolution, do you mean like how good the picture looks or
sorry,
uh,
let me clarify
small
that.
details? Yeah.
So going back to this kind of a thing, right, where I show you each of these individual grid cells where I solve my equations, the total, I would call the number of those cells the resolution. So it's the same as sort of like a pixels on a television.
Gotcha.
Each
Thank
cell
you.
is able to tell you something different. Um, but as you increase the number of those cells, you increase the model fidelity, you increase what you can capture, but you increase the cost. So we have, medium-ish resolution simulations that can run in real time or faster than real time, a few times faster than real time. Um, I think that being able to, I think there's a lot of software work that one could do with funding and time to make them even faster, whether you order, factor of order unity at least. Um, so I think you can certainly create configurations you could run in real time. But our highest resolution ones, probably not. And I think, for some of the ones that we really want to add all the bells and whistles of to understand an event that's already happened and reconstruct the magnetosphere during an event like that, those are harder to do. Those cost much larger compute requirements. But, for instance, I think it's not uncommon for like National Weather Service to run, a dozen models with a few hundred-ish compute cores each. And we could probably do some, a few hundred compute cores, we can do a version of the model that can run faster than real time.
That's really cool. Really, really cool. Thank you. Um, okay, so my other question is a lot of times when we talk with students, we get questions about getting involved in all of this through physics, which is fantastic. But we also get questions from people who aren't interested in becoming a physicist. And it sounds like the system of systems of teams that you have involve a lot of interdisciplinary interests. Can you speak a little bit to other ways people can get involved
Yeah, so
besides becoming a scientist, this physicist scientist?
yeah, sure. Yeah, here I think I put it. We have, I guess some of these are, of course, just scientists. Uh, Computer science we need. We have software engineers that we work with. I'm by training a mathematician, although I think I've been pretending to be a physicist for long enough where I probably count as one now. We have data scientists we work with. I think if having more and more visualization people that we can work with regularly would be fantastic. Having people who are better at really just helping us connect with the public about what we're doing and why it matters is, of course, important. Communication and outreach, and creating that barrier, that layer in between science and sort of the outreach. So I think all of that's really important. I think there's a lot of work that goes into that that is not just, solving nonlinear differential equations. Although that's, the most fun part, I think.
Thank you. As someone who's generally terrified of math, this is actually really helpful because it shows me what math can do.
Mhm.
It's not just equations existing in the ether, that they're wonderful things for this.
Yeah.
Go on ahead, Vince.
Yeah, I have a question about the auroral beads
Uh,
uh, slide. I think that I've probably talked to you about this at some point, but
yeah.
what are the scale sizes of aurora that you can reproduce in the model? Because it looks like
Mhm.
you have this 100-kilometer scale there. Um, and I mean, auroral beads can be spaced out that large, but usually they're a little bit smaller than that. Like the wavelengths are a little smaller. So is that just a
They're
limit of
already
the
getting
resolution?
they're
Or
already
is
getting
that,
smaller, it was my understanding. But yeah, I think it's resolution. You can sort of see here that we are, oh, sorry, if I can just play it. But yeah, you can sort of see here in the simulation we're sort of really getting down to these sort of spatial scales here of a handful of grid cells. I also think too, there's probably other physical processes that are going to start to play a role in exactly what's setting the minimum spatial scale of these that start to get more kinetic than fluid.
yeah. Okay, cool. Yeah, I mean, I've done this huge statistical study of beads. I've now finished it basically. I have 234 events, and usually, yeah, the wavelengths are a little smaller, but there are some events where the beads start out small and then they evolve into these larger, like kind of almost like curls, and those wavelengths are quite large, like on the order of sometimes 200 kilometers.
Yeah.
So, is it possible that in this simulation you're capturing more of the late stage bead?
I think,
And
yeah,
yeah,
it's quite possible that that's the case. It's quite possible that there's a kinetic branch of the instability that we're not fully capturing, and then we're only jumping in when we get to sort of the fluid scale portion of the plasma instability. Um, there's potentially also issues in terms of, do these fluid scale instabilities further break up after? Do they start big and break up into small? I think there's a question too, this is what's happening in the magnetosphere, and it's not a given that you will immediately see what's happening in the magnetosphere as auroral beads. It's only when you start to get the right precipitation from it. Could you get some of these plasma instability happening in the magnetosphere before you're starting to see enough precipitation to have a visible component to it? I don't know.
If there's time, could I ask another question? This is Jeremy. Um, I want to ask about model validation. So the two parts of that would be, uh, do you start, for example, with the beads? Are you familiar with a phenomena like the beads, and you're looking to reproduce that with the simulations in order to validate the simulations? Or is it the other way around, where you see something like that emerge from the simulation and you're able to then match it up with an observation? So sort of, I understand it would sort of go both directions, but what directions do you start with and how do you prevent?
It is, so
Uh,
that's a fantastic question because what it comes down to is, like I said, we don't have the initial condition of the system. We don't have the boundary conditions of the system. If I get in the model a wiggle in the aurora, the chances of that actually being the exact wiggle that somebody would have seen on the ground is not very high. Probably even if I had all of the right physics, or all the right physics and all the right boundary conditions, that would still be quite challenging, and I had none of that. To give an example, this is do I have it here? I think I do. Here I'm showing, this is from some of the work we've done on auroral giant undulations. This is showing data from DMSP, so spacecraft-based imaging. You can sort of see here towards dusk, this structure here in the equator word undulation. This is taken from the model, the same simulation. I think it's not exactly the same time, like 5 or 10 minutes apart, and it's in the wrong place. But if you zoom in using a same size box, you get pretty similar, I'd say, spatial structure in there. And so In this case, I would say that the model is reproducing the same kind of underlying physical processes that are at play. This is not a forecast, it's not a prediction, but I think we can use this to understand the kinds of things that happen in the magnetosphere to that are connecting to this in the Aurora. Before we had weather prediction, we had physics-based models that you could use to say these are the kinds of things that create a rain in a location, but not this is the chance it's going to rain at this location in this 2 days from now. And we're very much in the former case.
Thank you very much.
Yeah, thank you.
Does anybody else have any questions? We are right at time. Well, I know I could keep asking forever. This is so cool. And as a gamer, it's just really, really neat to see, first of all, your references, but also being able to visualize these things in a way that makes sense to me. And I absolutely love that. So thank you so much, Kareem. I really, really appreciate you being here with us today and look forward to hopefully having you work with some Aurorasaurus data sets in the future sometime.
Absolutely. Thank you so much for having me. It was
Thank
great.
you, everybody.